Okay, welcome my friends. Today we're going to talk about continuous exponential growth and decay. We have talked about the compound interest formula, and we even talked about what happens if your bank compounded your interest so fast, a billion times per second, that it basically became always continuously compounding. We had this formula. A PERT is kind of how you sum it up usually. But the limit of the compound interest formula, the limit, which I know is a limit is a topic you don't know a lot about yet, but it approaches this number E, and this is the value that will be what if we compound continuously. If you look at most textbooks, you will have a version of this for continuous growth and decay. Usually it has to do with half-life or bacteria growth, as these two examples show. But it's basically the exact same thing. If you have an amount of money that's continuously earning an interest rate, a certain percentage, that's the same as taking a big chunk of radioactive material and plopping it down on the table, and it continuously disintegrates. Or bacteria, if you have a petri dish and they're continuously reproducing, these both act the same way. Sometimes you'll see it as CE to the KT, or I believe our textbook has AE to the KT, but I want you to know that these are all the same thing. So I personally just think APERT each time, and the letters will kind of just stand for different things. So let's get to this first one. Radium-226, after 500 years, has decayed to 80.4% of its original mass. Find the half-life. So you'll get used to the different styles of these questions, but they all basically start here, and we'll fill in the info that we have and find the info that we don't have. So usually with this radioactive material, the rate, it's just something that has, that's unique for that material, that element or whatever. That's like the interest rate that's usually given in an investment problem, but we're not usually going to know this R value, or K if you use a different version of this equation. But let's figure out what we do know. We were not told how much we started with. So a cool thing about these problems is it does not matter how much we started with. If we started with P sub 0, like the initial amount, we know that we have 0.804 P sub 0 left after this amount of time, 500 years. T is 500, R is the number we do not know. Now, I don't need to know P sub 0, because if I divide both sides of this equation by P sub 0, it's going away anyway. So the important factor is that the amount is 0.804 compared to whatever we started with. If we started with 1 pound, then we have 0.804 pounds, but that P sub 0 cancels anyway. So here's where we stand. 0.804 equals E to the 500 R. All right, so now we do some calculating to figure out what is this R value. So I see that my unknown R is up in the exponent spot, and my base is E, which calls for a natural log of both sides. The natural log of E to the 500R is 500R. I'm going to divide by 500 on both sides and figure out what my R value is. All right, so that's natural log 0.804 over 500. Make sure you close those parentheses. So this kind of interest rate for this particular radioactive material is this. You see it's negative because it's decaying, and it's a very small number. So this is times 10 to the negative fourth. So I'm going to call this 0.000436. And I'm just going to leave it in my calculator, but on paper, and you don't want to round off early in these problems, especially exponential problems. You could create huge errors at the end of the problem if you use constants that are too rounded off. So that's usually how you're going to start one of these problems, with finding the rate, finding the quote interest rate, but for this material, even though it's not money. So now back to the original question. What is the half-life? All right, we talk about radioactive stuff in half-life. If I put a pound of it down, how long is it going to be until there's a half a pound left? So again, it doesn't matter what I start with. What I want to know is, when will I have half of that much left? This time, R I do know. I'm not going to write out the whole number, but my question is, what is T? So how long is it going to be until I have 0.5 left? 0.5 of what? It doesn't really matter, because like over here, that initial amount's going to cancel out anyway. So how do I solve this equation for T? So first I'm going to natural log, and you will end up doing natural log of 0.5 all the time, equals RT. Remember that I know R. So the natural log of 0.5 divided by this R value should be my answer. Natural log 0.5 divided by, I'm just going to go up or use my answer, second answer, and this is my answer, 1,588.65 years. And always look and make sure this is reasonable. If I had 80% left after 500 years, it's reasonable that I would have half of it left after almost 1,600 years. It's not out of the question. All right, so on the question like this, find this rate, this R value, and then use it to go back and answer the original question. Okay, so let's do a growth. We have bacteria growing on your kitchen counter, doubling every 5 minutes. That's nasty. Assume you start with only one. How many bacteria could be present at the end of 96 minutes? Again, probably not the most proper way, but I'm more comfortable learning one formula and getting good at it than worrying about what the different letters stand for. You've got your final amount, you've got your starting amount, you've got your rate, and you've got your time. I'm okay with it. All right. How many will be present at the end of 96 minutes? Okay, so if I start with 1, and I don't know this rate again, right? I don't know this R value, this constant number that applies to this certain bacteria. But I do know that if I started with 1 and it doubles in 5 minutes, that this is the equation to solve for that rate. Start with 1, end up with 2, 5 minutes later. And it's not like this has to be in years. It's just that if you start with minutes, end up with minutes. So divide both sides of this equation by 1. Basically, this 1 goes away. I get 2 equals e to the 5r. Natural log both sides. And r is going to be the natural log of 2 divided by 5. All right, so I can go ahead and I could express it that way, or if I wanted the decimal, natural log of 2 divided by 5. So this is my value. All right, this is growth, so I have a positive number for this rate. It's like an interest rate of 13.8% at the bank. I'm just going to save that again. So now back to the original question. How many bacteria could be present at the end of 96, assuming this same growth took place? Start with 1, e to the r times 96. And this one's pretty straightforward. If you're figuring out how much is left at the end, I don't need to do any natural logging. I just need to type in basically e to the r value times 96, where the r value is that number I just found. So that would look like this. E to the answer, second negative sign, reuses that old answer. A newer calculator, you can just go select that number, times 96, all in the exponent, where e is the base. And I have 602,248.8. Okay, so again, we're using APERT. It doesn't always have to stand for money. In my opinion, why learn different letters? It's all the same. Okay, so let's go back to money. This one, we're not going to, I'm not asking you the traditional question of how much money am I going to have if I invest this much. Let's reverse, and that'll just kind of change the order of steps that we need to follow. All right, so our friend Benny, he has got a bank account that will pay him 4.5% interest, compounded continuously, which is why I'm using A part and not the 1 plus R over N to the NT formula. He has a goal of $20,000, and he has 6 years to make that much money. So the question is, how much money does he need to put in the bank right now if in 6 years he's going to have 20,000? End up with 20,000. The principal, or the starting amount, that's what I don't know. E is just E, 0.045 times 6 years. Don't forget, a lot of mistakes happen by putting 4.5 instead of 0.045. All right, these need to be in decimal form. If you use 4.5, your answer is going to be ridiculous. So make sure you check the reasonableness of your answer. So now I need to solve for P. All right, so basically E to the 0.045 times 6, that's just a number that I can divide both sides of this equation by. So 20,000 divided by E to the 0.045 times 6 would look like this. Make sure you get the parentheses in the right places. You can do it a step at a time, but don't round off as you go. We have 15,267 and 59 cents. 15,267.59. All right, and that's reasonable. I mean, we make money in the bank, but in 6 years, you're not going to make a fortune. So if you put a little over 15,000 in the bank, you'll have 20,000 6 years later. So you made almost 5,000 for doing nothing. All right, so we are going to end there. These examples are all APERT. You should be able to solve for different unknowns throughout the formula. Remember, on these radioactive type questions, a lot of the time you're going to cancel out these doing things like this. So don't feel like there's information that you weren't given. You just have to use the information you were given correctly. All right, so that's going to do it. Exponential growth and decay. Young out.